you heard about fire and the future, and Dan McLennan from Environment and Climate Change Canada will talk to us about the contribution of fire smoke to air quality. So we've heard at this meeting for many years we had a lot of success with reducing, let's say, more traditional sources of air pollution, but now we have this newer threat of wildfire smoke. So Dan.
Hello everyone, my name is Dan McLennan. I'm an air quality scientist with Environment and Climate Change Canada. Part of the MSc in the Prediction Services and Operations West in the Air Quality Science Unit. I'm here to talk about the changing contribution of wildfire smoke to air pollution in Canada. So brief outline, we're going to speak to air pollution in general in Canada and how we've been working towards emissions reductions over the years. We'll talk about air pollution's emissions inventory, the impact of wildfires on air pollution, and some of the low-cost monitors that are helping to fill monitoring gaps. So this Health Canada report shows that the total economic value of adverse air pollution health impacts was estimated at $120 billion per year in 2016 dollars. Health Canada estimates that in 2016, 15,300 premature deaths could be attributed to air pollution, mainly in PM 2.5, nitrogen dioxide, and ozone. Air pollution impacts all Canadians, with the largest impacts in the most populated provinces, with the largest emission sources, those being Ontario, Quebec, British Columbia, and Alberta. And who is at greatest risk? It's people with existing lung and heart conditions, children, and seniors. Whoops. So I want to talk briefly about some reduction mechanisms. This is by no means an exhaustive list, but the National Air Pollution Surveillance Program was designed to provide accurate long-term air quality data of a uniform standard across Canada. It started in 1969. So if you actually want to know if air pollution is decreasing, you need to have those accurate long-term measurements to be able to evaluate that. The Canada-US Air Quality Agreement was signed in 1991 to address transboundary air pollution leading towards acid rain. The Canadian Environmental Protection Act is aimed at preventing pollution and protecting the environment and human health in 1999. The Canadian Council of the Ministers of the Environment is an intergovernmental collaboration that's also designed to align efforts to improving the environment. One of the major things to come out of that was the Air Quality Management System in 2012. And from that, we've established the Canadian Ambient Air Quality Standards, base level industrial emission requirements, and split the country into air sheds and air zones for management. And more recently, in 2021, there was the Active Transportation Fund, which was designed to increase opportunities for people to have active modes of transportation, thereby decreasing the amount of traffic on the roads and emissions. And the Zero Emission Transit Fund, which was money designed to change the fleets of public transit and, again, reduce emissions. So the air pollution's emissions inventory is another tool, and it's an annual report of anthropogenic or man-made air pollution emissions across Canada since 1990. It's developed with data from the National Pollutant Release Inventory, which is reported on by individual facilities, and it's supplemented with science-based emissions estimates. And they track 17 pollutants related to smog, acid rain, and poor air quality. And it's split into different categories of heavy metals, polycyclic aromatic hydrocarbons, persistent organic pollutants, and criteria air contaminants. And what it does is it attributes these emissions to various emission sectors such as agriculture, transportation, oil and gas, etc. And it's another tool for tracking the progress on air quality management strategies, policies, and regulations. So here I've just got a plot of the inventory's emissions from 1990 to 2021. And we can see we've got plotted sulfur oxides, VOCs, NOx, and PM 2.5. And we see that there have been significant reductions in sulfur oxides, mainly due to ore and mineral industry reductions, electric power generation in oil and gas, and also marine fuels. We see the decreases in VOCs and NOx, mainly due to transportation sector and increased vehicle stringency on regulations. And PM, on the other hand, is kind of a less convincing trend. And it's important to note that, again, these are only anthropogenic emissions and primary emissions, so any kind of atmospheric chemistry doesn't factor into these values. So wildfires, as Piyush just went over, are a naturally occurring hazard which can destroy life, property, resources, and infrastructure. Wildfire smoke poses considerable health risks. Vulnerable groups, including folks with pre-existing heart and lung conditions, again, children and seniors, and people who work outdoors. But everyone is at risk regardless of their age or health. And the fuel that's burning, weather, and burning conditions have varying impacts on smoke production and the emissions. So your fuel, the type of fuel, the moisture content, the weather, whether the fire spread is wind-driven or convection, and the actual burning conditions, if it's a surface fire all the way up to a crown fire, it all has varying impacts on what's actually being produced. So smoke itself is a mixture of water vapor, particles, and gases, including heavy metals, mercury, lead, cadmium, criteria air contaminants, NOx, VOCs, sulfur dioxide, ammonia, PM, carbon monoxide, polycyclic aromatic hydrocarbons, and also greenhouse gases such as CO2 and methane. And with photochemical reactions, those VOCs and NOx can end up turning into ozone as a pollutant and secondary organic aerosols. So given ignition, a fire actually spreads from heat transferring from the flaming front to the materials in front. And the first kind of phase of that is a distillation phase, or it's the drying out of fuels ahead of the flame, and that's been associated with VOC emissions. Next comes the pyrolysis phase, which is a low temperature decomposition of biomass into volatile gases and reactive char. So you get some oxygenated VOCs, carbon monoxide and carbon dioxide from that process. Next comes char oxidation, which is a smoldering combustion, which creates flammable gas mixtures of incomplete combustion products. So things like carbon monoxide, methane, ammonia, non-methane hydrocarbons, and PM are associated with that burning phase. And then next we move on to flaming combustion, which is the gas phase reduction of the emissions produced in the pyrolysis and char oxidation phases to produce large amounts of highly oxidized compounds and aerosols. Again, CO2, NOx, SO2, and particulate matter. So burning can kind of be split into two different types, where you've got flaming combustion, which is a more complete combustion with higher emission factors of carbon dioxide and NOx. I've got a study by Pritchard et al. Here. I've got SO2 and asterisks because his particular study indicates that the smoldering phase has a higher SO2 output, whereas other stuff that I've read provides the opposite. But anyways, the convection from these big flaming burning types can entrain emissions from each of these different burn phases with the potential to lift it high up into the atmosphere and transport it longer and farther distances. That's in contrast to the smoldering phase, which is a less complete combustion and creates generally more toxic pollutants. It has higher emission factors for carbon monoxide, methane, ammonia, and PM 2.5. And it may comprise 50% or more of the biomass consumed in boreal fire events, which will become more important later in the talk. But those smoldering fires lack the convective energy to actually lift those pollutants up and away and farther away from the source. So it's generally shorter range for these smoldering fires, and they end up burning slower and longer. So here I'm looking at a recent publication from Meng et al., and what we're seeing in the pie chart on the top is the wildfire contribution to PM 2.5 in Canada. And this is a snapshot evaluating the PM 2.5 contributions from different emission sectors using the GEOS Chem model for 2013. And what we can see is that wildfires were determined to be the leading cause, or leading sector, contributing to population-weighted PM2.5 exposure in 2013. The chart on the bottom left is showing that as the proportional contribution from power generation, agriculture, and industry is decreasing, the contribution from wildfires is increasing. And that's consistent with what they're showing in the total dry matter over top of Canada for the 1990 to 2015 range. So this other study by Schneider et al. Utilizes back trajectory from NOAA's high split model and satellite hotspot data to split the NAPS data set from 2001 to 2019 into days that are and are not influenced by wildfire. The plot on the lower left is showing data points for each of the different stations in the study, and it's the average value of fires impacted data on the y-axis and data that is not influenced by fire on the X. And what's in the black line is just the one-to-one line, and it's showing that PM, NOx, and carbon monoxide are all associated with increased concentrations due to those wildfires. We see less of a consistent trend on the influence of ozone as it's a secondary pollutant, and the age of the smoke reaching the sensors, and the amount of photochemical reaction that's happened impact it, so those connections are not quite as linear or obvious. Here's another figure out of that study. I've actually had to dig into some of the supplementary material to produce this, but what the plots are showing is the percentage of observations between May and September that were influenced by wildfires in each of the stations here. We can see the differing scale from Kamloops and Calgary to Vancouver being up around 30%, which are indicative that Kamloops and Calgary have had a larger percentage of smoke impacted periods than Vancouver. What we see particularly for Calgary is the frequency of these events. We can see that 4 of the top 5 values happened since 2014, so there's potential that it's an increasing trend there, but more data is needed to potentially make that assumption. So I'd like to first thank Jack Chen for getting me access to this data. This is from Environment Canada's model Firework, which is our air quality and smoke model. And what it does is it takes satellite hotspot data and combines it with the CFEP's emissions model, and it runs our weather model moving that emission from those fires forward in time. And what I've done is I've analyzed the number of days in each pixel that's exceeding the daily PM2.5 CAKES value of 27 micrograms per cubic meter. And one of the obvious trends that we see is generally impact in Western Canada. From 2018 all the way to 2023, there are impacts from wildfires in Western Canada, whether they're coming from fires down south in California or north in Alaska or homegrown in Canada. There's impacts there. And the 2023 is showing what an extreme fire season it was, with extreme impacts in northern Alberta, northern BC, and Northwest Territories, with over 50 days between May and September exceeding that CAKES value. So this kind of pairs well with how busy our forecasters have been over the last years, and we're looking at, in this figure, thanks to Melissa McDonald with the Health and Air Quality Program, the total number of days where special air quality statements were issued for each forecast region in Canada. Now this will also include stuff like smog events, because it's not limited to just the fire season, but from my experience in analyzing some of these on my own, it's primarily because of wildfire smoke. And again, it's showing the same trend in Western Canada, having these kind of extreme reactions compared to Eastern Canada. Also plotted on these plots are the actual areas burned for each individual fire season, which you might not be able to see at this scale, but I wanted to highlight 2023 in particular, where we can see first off in northern Alberta 135 days there was a special air quality statement. That's the equivalent of roughly 4 months of time that you're under an advisory that the air quality is not safe for you to go outside. When we look at the actual area burned, we see, as Push had mentioned, a lot in northern Alberta, northern BC, Northwest Territories, and also lots out in northern Quebec. But if you look closely in Manitoba and Ontario, there were some wildfires, but they weren't quite as big, yet we're still seeing these elevated air quality impacts. And that's because of how much that smoke from the Alberta fires has been spreading eastwards and blanketing the rest of the country. So what I've got here is, again, that air pollution emissions inventory plot that I had showed before. And I've done a little bit of lazy modeling and created estimates for 2022 and 2023 by just extending the values from 2021. And what I have plotted here is the cumulative emissions from firework from 2016 to 2023. And I just wanted to show that scale of how much that wildfire is actually contributing when you compare to the estimates from the rest of the other pollutants. So how does that actually compare with the data? I'd like to thank Jillian Chapman and Caitlin Badali with NAPS for getting me into this data set. What I've got plotted on the left is the number of stations in each province that are exceeding the annual 2020 PM2.5 cake standard, which is 8.8 micrograms per cubic meter. And the plot on the left is showing all data considered, whereas the plot on the right is showing data with the probable wildfires removed. And that wildfire removal process was determined by a combination of verification by the submitting bodies, the actual provinces, and by using statistical outliers that were within close proximity to forecasted smoke locations to remove them as smoke impacted days. And what we see is a very drastic change in Western Canada for those exceedances, in that they are so heavily impacted by wildfires compared to Eastern Canada. Also on this slide, we've got the boreal forest, which is something that Push showed earlier today, and areas burned from 2016 to 2023, along with the NAPS continuous PM2.5 stations across the country. And what I just wanted to show here is that while NAPS does a great job of representing the most populated places, we can see that spatially there are quite a few gaps in their monitoring. And that's something that Environment Canada has been working towards rectifying. In 2018, Environment Canada initiated a pilot project exploring how useful low-cost monitors would be in augmenting PM2.5 measurements for the Air Quality and Health Index forecast. We can see that the cost of the FEM instrumentation, being roughly $50,000, is preventative to expand the NAPS network out to much larger scales, whereas low-cost monitors at roughly $300 offer a unique opportunity to vastly improve the coverage at a slightly lesser data quality standard. There were 281 FEM stations in or near Canada with PM2.5 continuous measurements. 80% of the population and 25% of the communities within 25 kilometers were within that shorter distance of FEM monitors. So it is covering a large percentage of the population. But with the 1,500 Purple Air low-cost monitors that we have set up in Canada right now, with roughly a third of those being part of this pilot project, 91% of the population and 51% of communities are now within 25 kilometers of a Purple Air or an FEM sensor. Now, while Firework does an excellent job at modeling, there are missed events, and there is, due to a number of reasons, whether hotspots are obscured or just the weather forecast wasn't great. What we're showing here is the utility in these Purple Air sensors, which are the round dots on the map, how they can be used in an operational sense to identify where smoke plumes currently are versus where they were forecasted to be. So we can see in southern Manitoba there that they've obviously got significant smoke at the surface, whereas if we looked over northern Quebec, we can see kind of that forecasted smoke plume in the north maybe didn't mix down or didn't end up there, and perhaps ended up farther south in southern Quebec and Ontario there. So that's the kind of usefulness of these small sensors. We know that inequities exist in rural and Indigenous communities. We can see that purple air sensors and these low-cost monitors are helping to close the gap. What we've got plotted on the left side is the percentage of the population from the 2016 census that's within 25 kilometers of an FEM sensor only in the yellow bars, or an FEM and a PM 2.5 sensor in those yellow and purple stripe bars, and stuff that's within 25 kilometers of a purple air sensor only in the purple, and stuff that is outside of that 25 kilometer range in the dark red. We can see that there are still some significant gaps, but the purple air sensors are helping to close them. On the right plot, we're looking at communities within 25 kilometers of a monitor, and we see that there is still quite a disparity with a 30% difference between urban and rural, and still less than 50% of the Indigenous communities across the country are serviced, but that is something that we are actively working on and working with partners to get sensors out to everyone. So I'll touch briefly on how climate change is going to factor into all this, which Piyush has mentioned already, but here's just a quote from a few papers. First from Flanagan in 2006. In the future, under a warmer climate, we expect more severe wildfire, more area burned, more ignitions, and a longer fire season. And from Canadell et al. In 2021, the increase in forest burned area is consistent with increasingly more dangerous fire weather conditions, increased risk factors associated with pyroconvection, including fire-generated thunderstorms and increased ignitions from dry lightning, all associated to varying degrees with anthropogenic climate change. Here from Watton et al. In 2010, overall, across Canada, our results from the Canadian Climate Centre's general circulation model scenarios suggest an increase in fire occurrence of 25% by 2030 and 75% by the end of the 21st century. And then Burke et al. In 2023, we find that since at least 2016, wildfire smoke has influenced trends in average annual PM 2.5 concentrations in nearly 3/4 of states in the contiguous USA, eroding about 25% of previous multi-decadal progress in reducing PM concentrations on average in those states, equivalent to 4 years of air quality progress, and more than 50% in many Western states. So with more fires, we're expecting more emissions and more smoke. So climate change is predicting that it'll be worse in the future. So in summary, poor air quality is bad for human health regardless of the source. Wildfire smoke contributes significantly to poor air quality in Canada, especially in Western Canada, and it threatens to diminish gains made through various reduction mechanisms over the years. Climate change is predicted to make wildfire more common and therefore smoke more common. Low-cost monitors are helping to provide information on smoke impacts in smaller, remote, and rural and Indigenous communities across Canada. Here's a link to Braden's air quality map. And I'd just like to give a shout out to the low-cost monitor project collaborators, as it's a team effort. We couldn't do it without everyone's efforts. So, thank you.
Thanks, Dan, very much. Very full information, full of great information. Chris.
Maybe I'm not as loud as Sarah, but I'm close.
Maybe wait, because I think for people online, it's great.
Good morning. Thanks, Dan. That was wonderful. Could you comment on the choice of 25 kilometers as the metric for the coverage data that you showed?
Yeah, it was, as far as I know, somewhat a random choice. Braden Nilsson, I borrowed those slides from him, but I believe it's just, I think it is hard to generalize air quality over large scales, but 25 kilometers seemed as somewhat meaningful value to choose as opposed to hundreds of kilometers away. So, yeah, air quality is such a spatially varying issue. Going much smaller, you lose bigger chunks of your population. So I think it's just a value that we chose.
Other question, but I was trying to make sure I didn't ask two and other people. Are other people going to?
Go for it.
It's a much broader question, but I thought I'd ask because there was a comment towards the end, maybe in the summary, and I'm putting you a little bit on the spot, but you're in a different world than me, so I value your perspective on this. When you said that air quality is bad for everyone, which I agree, regardless of the source, I'm just curious from the community you work in, how important is it to know the difference in health effects between fire smoke and, say, traffic? And like, what would that mean to you from the community that you work with, which is different from mine? Like, how I agree with your comment, but if they're not quite the same, how might that be important, and what might you do with it? It's a kind of a big, difficult question. I appreciate.
Yeah, it's a little bit outside of the area that I'm actively working in, but yeah, we've seen that the emissions from wildfire smoke are so toxic, and I mean there are urban sources that are toxic as well, so they are important. But generally, seeing the scale of wildfire smoke and how it can impact such longer distances, it's important to be able to track how that is going to change and impact places in the future, because it is going to be becoming more and more frequent.
Right. Thanks very much.